In the vast expanse of the cosmos, a celestial event of unprecedented significance is unfolding. You might think you understand speed when you hear the figure 68 kilometers per second, but that's merely the beginning. That's 151,000 miles per hour, the velocity of a mysterious interloper from deep space. This isn't just any ordinary cosmic visitor. It's the third confirmed object to originate from beyond our solar system, earning the name 3I Atlas. Discovered on July 1st, 2025 by the Atlas telescope in Chile, a faint smudge against the star field caught the attention of astronomers. This smudge, 420 million miles away, was not abnormal in its brightness, but its trajectory was anything but ordinary. With a hyperbolic orbit and an excess velocity of 58 kilometers per second relative to the Sun, this object was on an escape trajectory, having enough speed to leave our solar system behind. By July 5th, confirmation came from observatories worldwide. Pre-discovery images surfaced from the Zwicky Transient Facility dating back to June 14th. Even telescopes as far out as 6.4 astronomical units from the Sun, already active and outgassing, had caught it in May. This object had been travelling through interstellar space for months before it was even noticed. Why was it so difficult to find? It was passing through the dense star fields of Sagittarius, right in front of the galactic centre, with thousands of stars per square degree. Finding one moving dot in that mess is like spotting a single firefly in a forest fire. As more data poured in, astronomers began to study this object in greater detail. Hubble caught it first in detail on July 21st, 2025, 277 million miles from Earth. The image showed a teardrop-shaped cocoon of dust, a coma roughly 18,800 kilometers wide, and a faint tail pointing away from the Sun. The nucleus, though small, was believed to be inside that glow. The measurements refined through August 20th, but the diameter of the nucleus was difficult to determine, ranging between 440 meters and 5.6 kilometers. Most likely it was less than 1 kilometer in size, small and dense, ancient and potentially rich in deep space chemistry. David Jewett at UCLA led the observations, stating, "You can't trace this thing back with any accuracy. It's like glimpsing a rifle bullet for 1,000th of a second. You see the trajectory, but not the gun." The comet had been travelling through interstellar space for billions of years. Gravitational interactions with stars and nebulae had scrambled its path, making it impossible to pinpoint the parent system. However, we know the direction. It arrived from Sagittarius, from the thick disk of the Milky Way. Matthew Hopkins at Oxford ran the numbers in July 2025 using the Otauta High Oxford Interstellar Object Population Model. The vertical velocity component is high, 18.5 kilometers per second upward through the galactic plane. That's not thin disk behavior. Thin disk objects orbit close to the galactic plane. Velocities under 10 kilometers per second vertical. Thick disk objects have tilted orbits, higher vertical speeds, older ages. Hopkins estimates 3I Atlas formed between 7.6 and 14 billion years old with 68% confidence. Independent analysis by Ostatler and Darrell Seligman in July 2025 agrees with a formation age of 3 to 11 billion years. Older than the solar system by at least 3 billion years, possibly by 9 billion years. This comet formed when the universe was less than half its current age. It orbited a star that may have died billions of years before Earth existed. It's been drifting through the void ever since. As the comet approached the Sun, it began to show signs of activity. On August 6, 2025, the James Webb Space Telescope turned its near-infrared spectrograph on 3I Atlas, distance 3.32 astronomical units from the Sun. The spectrum spans at 0.6 to 5.3 micrometers. The results shattered expectations. Carbon dioxide dominates the coma. CO2 to H2O makes them ratio 7.6 plus or minus 0.3. That's 8 to 1. Carbon dioxide to water. It's the highest ratio ever observed in a comet at that distance from the Sun. The spectrum also shows water ice, water vapor, carbon monoxide, carbonyl, sulfide, and dust. But carbon dioxide is king, 87% of the gas by mass. Water makes up 4%, carbon monoxide 9%. This isn't how comets work in our neighborhood. Solar system comets supplement water as their primary volatile. Water drives the activity, creates the pressure, lifts the dust. But 3I Atlas runs on dry ice. The carbon dioxide sublimation rate at 3.32 astronomical units suggests an intrinsically CO2-rich nucleus. Either it formed far from its parent star, beyond the carbon dioxide frost line where temperatures allow CO2 to freeze, or it was exposed to extreme radiation that processed the ices over billions of years. Cosmic rays can break molecular bonds, alter ratios, create chemical signatures we don't see in young objects. The Spherex Space Observatory confirmed the finding in mid-August 2025. Detection of bright carbon dioxide emission and water ice in near-infrared bands. The 1 micrometer flux suggests a large reflecting surface. AV Low calculated a diameter of 46 kilometers based on that data, though he notes the mass discrepancy. If true, 3I Atlas is 46 kilometers wide. Its mass would exceed the previous interstellar comet, 2I, and we should have discovered 1 million such objects before finding one of this size. The interstellar density of rocky material is too low by a factor of 10,000 to deliver a 46-kilometer object into the interstellar medium over 3I Atlas's decade-long survey. Either the nucleus is much smaller and surrounded by a dense dust coma reflecting most of the sunlight, or something else is going on. Loeb suggests checking with radio telescopes for technological transmissions. He's half joking, mostly serious. As the comet approaches Mars and Jupiter, the alignment is suspicious. 1 in 500 chance for a random interstellar object to match the ecliptic so closely. Avilobi notes this. He notes everything. The alignment, the mass, the nickel without iron, the carbon dioxide dominance, the trajectory toward Mars and Jupiter. He suggests checking for radio signals. Most scientists roll their eyes. Loeb doesn't care. He's been here before with Oumuamua. He'll follow the data wherever it leads, even if it leads somewhere uncomfortable. As 3I Atlas approaches Mars and Jupiter in October 2025, multiple spacecraft will coordinate observations of this interstellar object from another planet. This is historic and unprecedented. The data won't arrive for weeks, but the observations happen now. October 2025. While 3I Atlas races toward perihelion and Earth can't see it because the Sun is in the way, Mars watches from 30 million kilometers away. October 29th, 2025. 11:44 UTC plus or minus 1 minute. Distance 1.36 astronomical units, 203 million kilometers. 126 million miles, just inside Mars orbit. The comet will be moving 68 kilometers per second, 151,000 miles per hour. Escape velocity from the solar system at Mercury's orbit is 68 kilometers per second. 3I Atlas at Mars distance matches that. It's moving fast enough to escape from closer to the Sun than it actually is. Hyperbolic excess velocity, 58 kilometers per second. That's the speed it had when it entered the solar system. The Sun added 10 kilometers per second as the comet fell inward. At perihelion, total velocity peaks. After perihelion, the Sun's gravity slows it again. By the time 3I Atlas crosses Jupiter's orbit outbound in March 2026, it will be back to 58 kilometers per second relative to the Sun. Forever. The comet will never stop, never return. It came from the thick disk, passing through the thin disk where we live, slingshotting around the sun and heading back out. Trajectory tilted 5 degrees to the ecliptic. Retrograde motion, moving backward relative to planetary orbits. The alignment is suspicious. 1 in 500 chance for a random interstellar object to match the ecliptic so closely. Avilobi notes this. He notes everything. The alignment, the mass, the nickel without iron, the carbon dioxide dominance, the trajectory toward Mars and Jupiter. He suggests checking for radio signals. Most scientists roll their eyes. Loeb doesn't care. He's been here before with Oumuamua. He'll follow the data wherever it leads, even if it leads somewhere uncomfortable. November 2025. ESA's Jupiter Icy Moons Explorer will observe 3i Atlas for 3 weeks, November 2nd through 25th. Multiple instruments, cameras, spectrometers, particle sensors, coordination with NASA's Europa Clipper considered. Twin ultraviolet spectrographs, 1 on each spacecraft, compared notes, cross-checked measurements. JUICE sits on the far side of the Sun from Earth. Data transmission, slow. Using medium-gain antenna because high-gain antenna acts as a heat shield is close to the Sun. Results won't arrive until February 2026. But JUICE will see the comet in its most active state, fresh from perihelion, heated, outgassing, tail fully extended, coma, bright, broad, peak, carbon dioxide, sublimation, peak, nickel emission, peak cyanide production. The chemistry will be on full display. Whatever 3i Atlas is made of, whatever processes created its bizarre composition, JUICE will see it unleashed. December 2025. James Webb observes again. Hubble continues ultraviolet spectroscopy, monitoring composition as the comet retreats. Sulfur to oxygen ratio measurements, gas emission tracking. The telescopes will follow 3i Atlas until it fades below detection limits. Months, maybe a year. Depends on activity levels, depends on dust production, depends on whether the nucleus stays intact or fragments under thermal stress. Comments do that. 2. I Borisor fragmented. Broke apart near perihelion. Thermal shock. Structural failure. But 3i Atlas. C seems stable so far. No outburst detected as of September 2025. Brightness steady. Activity predictable. The nucleus might be tougher than expected, billions of years drifting through space, cosmic ray bombardment, micrometeorite impacts. The surface could be armored, centered, heat treated by interstellar radiation into something harder than fresh cometary ice. The composition tells a story. Carbon dioxide richness suggests formation beyond the CO2 frost line. In our solar system, that's around 5 astronomical units. Saturn's distance, in another system, depends on the star's luminosity. A dim red dwarf pushes frost lines inward, a bright young star pushes the outward. But CO2 forms farther out than water in any system. The ratio indicates a cold birth. Outer disk, where temperatures allow carbon dioxide to condense but water remains scarce. Or radiation processing. Billions of years exposed to galactic cosmic rays. Energetic particles slamming into surface ice. Breaking bonds, preferentially removing hydrogen. Water loses hydrogen easily. H2O becomes OH becomes O. Carbon dioxide is more stable. C equals O double bonds harder to break. Over time, a water-rich comet irradiated in interstellar space could become carbon dioxide-rich through differential destruction. The surface ice, as we see, might not match the interior. The coma might reflect processed surface material, while the nucleus holds pristine water ice underneath. That would explain the low water detection. A crust. A carbon dioxide-rich crust insulating a water-rich core. The heat from perihelion could break through, could crack the crust, could release the water. Well, no, in late October when 3i Atlas passes the Sun, and the Mars fleet watches from 30 million kilometers away, the thick disk origin matters. Matthew Hopkins's Otauta High Oxford model uses Gaia data, Milky Way chemistry models, and stellar kinematics. The vertical velocity component places 3i Atlas in the thick disk population. Stars there are older, metal-poor, formed when the galaxy was young, heavy element abundance at least 40% of solar. Lower metallicity means different planet formation, different disk chemistry, less dust, less rocky material, more ices. Giant planets form faster in metal-poor disks if they form at all. Comet populations differ. Composition shifts toward volatiles. Carbon and oxygen compounds dominate over silicates. 3i Atlas might represent typical thick disk comet composition, or it might be an outlier even there. We can't know until we find more. The Vera Rubin Observatory will help. Legacy survey of space and time starts soon. 10-year survey. I expected to find 5 to 50 interstellar objects per year. Maybe more. Depends on size distribution, depends on number density in the local interstellar medium, depends on our detection limits and survey cadence. But the sample will grow. We'll stop treating each interstellar visitor as unique. We'll start seeing patterns, families, chemical signatures, dynamical groups. We'll build a taxonomy of extrasolar objects the way we have for asteroids and comets. 3i Atlas is just the beginning. The adjustment changes everything. 7.6 to 14 billion years. The Sun formed 4.6 billion years ago. Earth 4.5 billion. Life on Earth 3.8 billion years at least. 3i Atlas predates all of it by billions of years. It formed when the universe was 2 to 6 billion years old, when the Milky Way's thick disk was assembling, when star formation rates peaked during cosmic noon. The parent star could be dead, could have gone supernova billions of years ago. The planetary system could be gone, destroyed, scattered, consumed. Only the comets remain, ejected during formation, kicked out by giant planets, sent into interstellar space. Wandering, 3i Atlas wandered for 10 billion years, give or take, circling the galactic center, drifting through spiral arms, passing thousands of stars, never captured, never destroyed, until July 2025, when it happened to pass through a tiny patch of space we're monitoring, 420 million miles from a yellow dwarf star in the Orion Arm, a star with planets. One planet with telescopes. We saw it, we're tracking it, we're measuring it. And in a few months it will be gone. Never to return, back into the dark, back into the deep, back to wandering the thick disk for another 10 billion years. Unless it hits something, unless another system captures it, unless it fragments, unless something we can't predict happens. But most likely it just keeps going. Silent, ancient, alone, the speed proves it. 68 kilometers per second at perihelion. That velocity doesn't happen by accident. That's not a gravitational slingshot from Jupiter. That's not orbital velocity, that's hyperbolic departure. The comet entered the solar system already moving 58 kilometers per second. The Sun added 10, it will leave moving 58. The kinetic energy is immense, mass times velocity squared over 2. Even a small nucleus carries gigajoules. If 3i Atlas is 1 kilometer across, and density is 500 kilograms per cubic meter, typical for comets, mass is roughly 2.6 times 10 to the 11th kilograms. Velocity 58,000 meters per second. Kinetic energy 4.4 times 10 to the 20 joules. That's 105 megatons TNT equivalent. The Tsar bomber was 50 megatons, the biggest nuclear weapon ever detonated. 3i Atlas carries twice that energy, just from speed. Impact with Earth would be extinction level. Won't happen. Closest approach 1.8 astronomical units, 270 million kilometers, 167 million miles. December 19th, 2025. Safe, totally safe. But the energy is there, stored in velocity, ancient kinetic energy from a birth system we'll never see. The silence from Mars was deafening. Not literal silence, but the radio silence of data transmission. For 2 weeks after the October 3rd flyby, the scientific community held its collective breath. The European Space Agency and NASA confirmed their Martian flotilla had performed flawlessly. Mars Express, the Trace Gas Orbiter, and the Mars Reconnaissance Orbiter had all slewed their instruments to track the fleeting visitor. On the surface, Perseverance and Curiosity had pointed their cameras skyward. But the data was a slow trickle, travelling across tens of millions of kilometres of interplanetary space. Queued and buffers, downlinked through the deep space network and routed to processing centres in Darmstadt and Pasadena, the world waited. And while it waited, 3i Atlas continued its next ribble plunge toward the Sun. By October 15, 2025, the comet had brightened magnitude 13. Still a challenge for amateurs, but a beacon for professional observatories. The green coma, fueled by diatomic carbon and cyanide, had swelled to over 200,000 kilometers in diameter. The dust tail, once a faint smear, now stretched over 1 million kilometers, a pale yellow ribbon against the black. The rate of change was astonishing. Ground-based telescopes reported the nickel emission had doubled again, now approaching 10 grams per second. Hydrogen cyanide production was a torrent, nearing 5 kilograms per second. The comet was shedding massive, a furious pace, a celestial iceberg melting not in water, but in a fire of its own volatile chemistry. The question on everyone's mind was simple. What did Mars see? The first high-rise image from the Mars Reconnaissance Orbiter was released to the public on October 18, 2025. It was at first glance a disappointment. A single, overexposed pixel, the core of the coma, was so bright, so dense with dust, that the super-high-resolution camera was saturated. The team at the University of Arizona had expected this. They released a second image, processed with extreme prejudice, filtering out 99.9% of the light. What remained was ghostly, not a single nucleus, but a tight cluster of at least 3, perhaps 4 distinct points of light, embedded in a shared teardrop-shaped haze. The primary object was estimated to be no more than 800 meters across. The companions were smaller, perhaps 100 to 200 meters each. They were tumbling, separated by only a few kilometers. 3i Atlas was not a solid body. It was a rubble pile, or it was in the process of becoming one. This changed the interpretation of the Hubble data. The earlier size estimate, between 440 meters and 5.6 kilometers, now made sense. They weren't seeing a single object. They were seeing a gravitationally bound swarm. This also began to explain the violent, asymmetric outgassing. The sun wasn't heating a single rotating body. It was cooking a collection of fragments with sunlight penetrating the gaps between them, heating surfaces that would normally be in shadow. It was a cascade failure in slow motion. Billions of years of interstellar travel had ended in a chaotic breakup just as it reached the intersolar system. Then came the spectrometer data from the Trace Gas Orbiter's Nomad instrument. The data confirmed the carbon dioxide dominance in spectacular fashion. The CO2 signature was so strong it drowned out almost everything else. But deep in the noise, after weeks of analysis, the team found something new, a faint but unmistakable absorption line from methane. And not just any methane, the isotopic signature was heavy. It was rich in deuterium, the heavy isotope of hydrogen. The deuterium to hydrogen ratio in the methane was staggeringly high, 5 times higher than any comet in our own solar system. This pointed to an origin in an extremely cold, dense molecular cloud, far colder than the nebula that formed our own sun, a place where deuterium could more easily bond with carbon, preserved in frozen methane for eons. The comet wasn't just old, it was born in a fundamentally different, colder environment than anything we knew. As perihelion approached, the tension was palpable. October 29th, 2025, and the day the comet would feel the sun's maximum fury. All eyes were on the solar and heliosphere OBs, Observatory, SOHO, and the twin stereo spacecraft. They were the only probes positioned to watch the close pass. As from Earth's perspective, the comet was lost in the sun's glare. Amateur astronomers were out of luck, but the world's solar telescopes were locked on. At 11:44, Coordinated Universal Time, 3i Atlas reached its closest point to the sun. 126 million miles, screaming past at 151,000 miles per hour. For 3 days, the data from SOHO's coronagraphs was a tantalizing mystery. The instrument, designed to block the sun's direct light to see the faint corona, showed a massive plume erupting from the comet's position. It wasn't a normal tail. It was a vast, expanding cloud, a coronal mass ejection, but in miniature, originating not from the sun, but from the tiny interstellar visitor. On November 1st, when the analysis was complete, the announcement came. At perihelion, the primary 800-meter fragment had disintegrated. The thermal stress was too much. The rapid heating caused subsurface pockets of frozen carbon dioxide and now, presumably methane, to flash vaporize. The pressure built until it exceeded the structural integrity of the ancient irradiated ice. The nucleus blew apart. The SOHO data showed the cloud of debris expanding at over 500 meters per second. The once coherent cluster of fragments was now a rapidly dispersing shotgun blast of ice and rock. 3i Atlas, the billion-year-old wanderer, had died in a blaze of glory. This event, however tragic for the object itself, was a scientific goldmine. The explosion had excavated the comet's interior, exposing material that had been shielded from interstellar radiation for billions of years. This was the moment the Jupiter Icy Moons explorer, JUICE, had been waiting for, positioned perfectly for the aftermath. JUICE began its 3-week observation campaign on November 2nd. Its particle detectors and ultraviolet spectrograph were aimed at the expanding cloud of debris. The first results from JUICE, received on Earth in slow, painstaking packets through its medium-gain antenna, began arriving in late November and were nothing short of revolutionary. The ultraviolet spectrum of the fresh material was completely different from the perihelion coma. The carbon dioxide signature was still there, but it was no longer dominant. Suddenly, water was everywhere. The H2O signal surged, becoming the most abundant volatile by a factor of 3. The theory of a processed carbon dioxide-rich crust insulating a water-rich interior was confirmed in the most dramatic way possible. The comet had worn a disguise, a thin layer of dry ice created by eons of cosmic ray bombardment. Its true heart was water, just like the comets of our own solar system. But the other mysteries only deepened. As JUICE's Janus camera attempted to resolve the largest remaining fragments, its particle detector, the particle environment package, began registering impacts, not just dust grains, but something bigger, microscopic metallic particles. The composition sensor analyzed them. They were almost pure nickel. The nickel without iron problem was not just a gas phase anomaly in the coma. It was a solid-state reality in the dust. The comet was shedding tiny flecks of refined nickel. Avalob's office at Harvard became the center of a firestorm of speculation. His earlier hot, half-joking suggestions about technological signals were now being discussed with a nervous sobriety. Natural processes that could create pure nickel grains in a comet were unknown. Could extreme radiation differentiate the elements? Could some bizarre chemical process in a protoplanetary disk create nickel-rich sulfides that release their metal content without iron? The theories grew more exotic by the day. One paper proposed that the parent star had been a rare type of supernova, an iron-poor core collapse event that ejected vast quantities of nickel and zinc. Another suggested the comet had passed through the debris field of an exploded alien artifact billions of years ago, collecting metallic shrapnel. Mainstream science pushed back, urging caution. We have a sample size of 1 for this kind of object. To leap to extraordinary conclusions is premature, but the data was undeniably profoundly strange. In December, as the expanding cloud of 3I Atlas crossed Earth's orbital path at a safe distance of 167 million miles, the James Webb Space Telescope had its second look. The near-infrared spectrograph was now pointed at a diffuse and faint ghost of a comet. The spectrum was a complex tapestry of molecules. The water and carbon dioxide were there, as expected, but Webb detected more ethane, up to methanol, and in trace amounts, complex organic molecules like all in a trial. The potential precursor to adenine, one of the 4 nucleobases of DNA. This wasn't entirely unexpected. Solar system comets like Hale-Bopp carried a rich inventory of organics, but finding them in a relic from a star system billions of years older than our own was a profound discovery. The building blocks of life are not unique to our corner of the galaxy. They are ancient, and they are interstellar. The chemistry for life has been available for a very, very long time. The Atacama Large Millimeter Submillimeter Array, ALMA in Chile, provided the final crucial piece of the puzzle in early 2026. By studying the microwave emissions from the cyanide molecules and the dissipating cloud, the ALMA team was able to measure the ratio of carbon-13 to carbon-12 and nitrogen-15 to nitrogen-14. Isotopic ratios are like fingerprints for cosmic objects, telling us about their birthplace. Our solar system has a very specific set of isotopic fingerprints. The ratios measured in the remnants of 3I Atlas did not match. They were consistent with the chemical evolution models of the Milky Way's thick disk, from a time 7 to 9 billion years ago. The comet was definitively a product of the old galaxy, an ancient mariner carrying the chemical memory of a long-dead star. By March of 2026, the story of 3I Atlas was functionally over. The cloud of its remains had grown so diffuse, it was undetectable by all but the most powerful telescopes. It was outbound, coasting back into the interstellar void at 58 kilometers per second, not as a single object, but as a trillion tiny ghosts. A diffuse stream of dust, ice and gas that will slowly spread out over millions of kilometers as it continues its journey through the Milky Way. So what have we learned? We learned that interstellar objects can be deceptive, wearing processed crusts that hide their true nature. We learned that the building blocks of life are widespread and ancient, present in star systems that formed when the universe was young. We learned that the chemistry of the old galaxy, the thick disk, is suddenly different from our own neighborhood, and we were confronted with a mystery, the nickel, that we still cannot explain. It stands as a stark reminder of our own ignorance. There are processes in this universe, either natural or otherwise, that we do not yet comprehend. David Jewett summarized best in an election in April 2026. He said, "We thought we were observing a bullet. It turned out to be a clay pigeon, shattering at the moment of peak illumination. But in shattering, it scattered its secrets across our sky. We will be analyzing the fragments of 3i Atlas for decades. It was a messenger that consumed itself to deliver its message. The comet is gone, but its data remains a torrent of numbers sitting on servers around the world. And those numbers are the clues to the formation of other solar systems, to the chemistry of the early galaxy, and perhaps to questions we haven't even thought to ask yet. The Vera Rubin Observatory will come online soon, promising to find dozens of these interstellar travelers every year. We will have more bullets, more clay pigeons. We will build a catalogue of these visitors, and the strangeness of 3i Atlas will either become a new normal, or it will stand out as an even greater anomaly. For now, it remains our most detailed, most explosive, and most enigmatic glimpse into the galaxy that lies beyond our own shores. A reminder that the universe is not only stranger than we imagine, it is stranger than we can imagine, and it's coming to visit.